Let us solve for the probability generating function from Poisson distribution. Remember that the generating function is equals to expected value of x, also equals to the summation of probability of x equals to x times s. Example, let x have a Poisson distribution with parameter lambda p. Probability takes value x equals to x with exponential power lambda power x and x factorial. X is equals to 0, 1, 2, and 3. Find the probability generating function of the distribution. We should remember that probability generating function is equals to summation from x is equals to 0 up to infinity probability x to x multiplied by x by s or x. Now let us find for our generating function, which is equals to summation of this value from 0 to infinity exponential power lambda power x over x factorial. Let us multiply this function with s. So when we multiply, we get our generating function is equals to summation from 0 to infinity exponential power negative lambda over lambda power x over x times lambda times sx. So when we take the exponential, since we do not have value of x in our exponential, we remain with the variable which contain x. You get that the generating function is equals to exponential power negative lambda summation from x is equals to 0 up to infinity is equals to lambda power x over x factorial multiplied by s power x. So when we multiply lambda x and x power x, we get that the generating function is equals to e power negative lambda summation from x is equals to 0 up to infinity is equals to lambda s, both of them powered by x over x factorial. Because we have 2x, this x cancel this x, so we remain with our generating function, our probability generating function for Poisson distribution equals to exponential power lambda summation from x is equals to 0 is equals to infinity is equals to lambda s. So when we multiply with exponential, we get that our probability generating function is equals to e negative lambda plus lambda power s. So when we substitute lambda, you get that our generating function is equals to e lambda minus 1 minus s. So with this, we can also be able to solve for the mean of the Poisson distribution. If we have been told to solve for the mean, we first find the first derivative of our probability generating function, which is lambda exponential lambda 1 minus s. Now suppose the value of s is equivalent to 1, therefore lambda exponential lambda power 1 minus 1, which is 0. We know that the generating function where s is equals to 1 is equals to lambda minus exponential power 0. Exponential power 0 is equivalent to 1, so the mean of Poisson distribution is equals to lambda. We can also solve for the variance of the Poisson distribution. The variance, we already know that the variance is equals to first derivative of the probability generating function plus the second derivative of the probability generating function minus the first derivative squared. So what we are supposed to do is to find the second derivative of this function. So when we do the second derivative, we get that the generating function of x is equals to lambda power e lambda 1 minus s. So when we do the second derivative, we get that lambda squared exponential lambda 1 minus s. So when we take the value of s equals to 1, if the probability generating function converge, you get that 1 lambda is equals to e power 0. So the second derivative of the probability generating function is lambda squared. Since the exponential power 0, when you insert it in your calculator, it will give you that exponential power 0 is equivalent to 1. So in order to get the variance, we shall take the value of the first derivative, which is lambda plus lambda squared minus lambda squared. So the variance is equals to lambda minus lambda, which is lambda, so our variance is also lambda. So we have been able to solve the probability generating function of the Poisson distribution.